Welcome back from spring break. I hope everybody had fun working on their class project proposals. I had fun reading them. I think I've sent everybody email now in response to them and have had some conversations about it, but by all means send more responses to continue the conversation. So I think we delayed the homework, so it's due Thursday. Is that correct? Okay, hopefully everybody can breathe a sigh of relief there. So today we're going to do one more of the several dwarfs, motifs, patterns that we've been talking about all semester. We're going to talk about how do you do parallel FFTs. And and I'm sure many of you know different applications for FFTs. I will mention a few. And I will also begin from scratch. So in case you haven't seen the fast Fourier transform defined before and derived, I will show you how it works very briefly so that we know what the sequential algorithm is so we can begin parallelizing it. And then I'll do the parallel 1D FFT. But it turns out that most people use it in higher dimensions. There are many applications use it in 2 or 3 dimensions. So I will do a dive into the 3-dimensional FFT and talk about the interesting design space that people have explored to make it go so fast. As much as in matrix multiply, so many people care about doing this particular operation, FFTs, an enormous amount of effort has gone into tuning it. And so in fact, there are 2 auto-tuning projects. FFTW, which is short for the fastest Fourier transform in the West, and Spiral, which actually tries to do all of signal processing, and they have a startup now to provide auto-tune versions of many signal processing algorithms on many different kinds of hardware. So all of this is important, so people have been exploring it, and I'll just do a little bit of overview of those auto-tuning projects. And there's lots of references, and here in particular are the pointers to the websites for those auto-tuning projects. So let me define the notation that I'm going to use. And I will try very hard never to use the letter I to be an index. It's always going to be the square root of -1 throughout this lecture. So let's remind me if I get that wrong. And all of our indices are going to start from 0 to make all of the indexing easy. And so the one-dimensional discrete Fourier transform of a vector is a simple matrix vector multiply, f times v, where the matrix f has a very simple definition. The jkth entry, and remember j and k start at 0 and go up to m-1, is a number, a complex number to the jkth power, where that number is a root of unity. So it's a number whose mth power is 1, and it's e to the 2 pi square root of -1 over m, and there it is. Right? So if I just did this in the obvious way, it would be an m squared operation, and of course, what the FFT lets us know how to do it in m log m instead of m squared. And that's what we're going to do. So in particular for m equals 4, in that case the mth root of unity is simply the square root of -1, and there are all the other roots of unity that are used. And so that's the one-dimensional case. I'm also going to do the two-dimensional case and higher. So the easiest way to define the two-dimensional Fourier transform, and if anybody's ever looked at a JPEG image, you've depended on this. This is how JPEG works. What we're going to do is take a matrix, V, and I'm going to do the Fourier transform to every column. So if I pre-multiply this matrix times f, I'm multiplying, that's doing the Fourier transform of every column of V independently. And then when I post-multiply by this same matrix, that amounts to doing the Fourier transform of each row independently. And so that's what the two-dimensional is. Do it to every column, then do it to every row. And because matrix multiply is associative, I can do it in either order. It doesn't matter. I get the same answer. That's the two-dimensional one. And of course, the three-dimensional ones are analogous. It's a little bit harder to write down using linear algebra terminology. But if I have a three-dimensional grid of data, what's the three-dimensional FFT? I take each one-dimensional slice in the x direction. I do all of those FFTs independently. Then I take each little vector in the y direction, do all of those. Each little vector in the z direction, and do all of those. So that's a three-dimensional FFT, and that's very common, and that's where I'll spend a fair amount of time doing optimizations. So I guess if you Google FFT, you will get thousands of applications for it. Let me just mention a few. It was perhaps most widely used in signal processing. I'll give you a one-slide example of why that solves a very basic filtering problem in signal processing. I'll give you another one-slide example of how it's used in image processing by sort of not really how JPEG works, but something that gives you the idea. And of course, in this class, it's all about Poisson's equation has been our running example. So I will show you how to solve Poisson's equation in nearly optimal time. Optimal would be order n, because there's n outputs. I will do it in multi-grid attain that. We did that last time. But with the Poisson, with using the FFT, we can do it in n log n. And depending on the relative speed of arithmetic and communication on your particular computer, it's not clear whether multi-grid is the fastest or the FFT is the fastest, so both are used. It's also the fastest algorithm for multiplying very, very long integers, and it goes on and on. But let me just give you some, let me just deal with the first three. So I'll run a very simple example. I'm going to take a signal with exactly two frequency components, sine 7t and sine 5t. I'm going to sample it at 128 points, and there it is, this nice wavy, smooth line. And now I'm going to make it noisy. I'm going to add a random number of size between -3/4 and +3/4 to every point. And I'm going to get this very, very messy signal, right? So this is what I can measure. This is what lies underneath it. I would like an automatic way to throw out all this noise and get back to the nice, smooth signal. So the FFT tells us how to do that. I will take the Fourier transform of this vector. Let's say I sample it at 128 points. I get a complex array, and there's the real part, and there's the imaginary part. The real part is all 0, and the imaginary part only has non-zero components corresponding to 7 and 5, because those are the two frequencies there. Now when I add the noise, this is what I get, this is what I measure. Then I do the FFT again. There's the FFT, the real part, and there's the FFT, the imaginary part. And now it doesn't look quite so noisy anymore, right? The real parts have noise spread out everywhere, but it's really quite small. And so my obvious filtering algorithm is going to be, I'm going to take the FFT and simply zero out any component that's small enough. And I'll just pick a threshold of about 1/4. So all of these numbers are well less than 1/4. So when I zero them out, maybe there are 2 little bits left. And everything becomes very smooth, and I get back what I started with. So this is sort of the canonical example of what FFTs are good for filtering. So that's a one-dimensional example. Now let me do a two-dimensional example. And so here, and so now I want you to think of an image. Here is an image of, that we look at every day. 200 by 320. So at each matrix entry, I have a number which represents, how much red, green, blue I have. And what I'd like to do is compress that by storing as little data as possible. So what I'm going to do is I'm going to do a two-dimensional FFT of this matrix. So each column of length 200, I'll do a 200-dimensional FFT of that. Then for each 320-dimensional row, I'll do that. And I get another matrix of complex numbers. And similarly to this idea, I'm only going to keep the largest entries. I'm going to keep the largest 2.5%, just for the sake of this illustration. So I'm throwing away 97.5% of the data. And that's all I'm going to store. How good is the image? That's what I get back. So it's not really perfect. So that's not exactly how JPEG works. But you can see this much information reproduces quite a bit of the image. And so this is another example. And finally, we get to Poisson's equation, which is the running example in the class. And so there are the three flavors of it. The one-dimensional case, which gives us a tridiagonal matrix, which I'll remind you what it is in the next page. The two-dimensional one, where we get a band matrix that I'll show you on the next page with 4s down the diagonal and some -1s. And then there's the three-dimensional version, which I won't try to write down, but I will show you how the three-dimensional Fourier transform is used for that. And it comes up in many, many places, but let me just remind you of the notation so I can say how to solve this really, really fast, the two-dimensional case. So here is the notation that we've used before. So here's the one-dimensional Poisson equation, system of linear equations. I'll use the 1 to indicate it's one-dimensional. So L1 is the Laplacian. 2's down the diagonal, -1's off, and so that's a stencil. I obviously don't store the 2's and -1's. And here is the two-dimensional version. And so I've written it this way. So I've written out every last entry. And so it's the x derivative is a -1, 2, -1. That's the x direction. In the y direction, it's also a -1, 2, -1. So there's a 4 there. So how do I take advantage of this matrix to use the FFT? And so here's the classic way we do it. I'm going to use two interesting facts. The first one is that if I take that one-dimensional matrix, 2's down the diagonal, -1's off, the FFT is basically its matrix of eigenvectors. This is just the fact. So I can factor that matrix into F times a diagonal matrix of eigenvalues times F inverse. And F inverse happens to be the transpose because it's a symmetric matrix, and so its eigenvectors, the inverse of this eigenvector matrix is just the transpose. F is not exactly the FFT. It's almost the FFT. It's basically the imaginary part. And so that's good enough for all my purposes. And D is a diagonal matrix of eigenvalues, and we can write them down too. So that's one mathematical fact that you can use trig identities to confirm. And the second fact is that solving Poisson can be written in this way. So I don't have to write it as a matrix times vector equals a vector. I'm going to write it this way. So X is a square matrix of unknowns. It is the unknowns in my two-dimensional grid. Multiplying it by L1 in front, that's transforming each column. That's the second derivative in the y direction. This multiplies each row of X times L1. That's the second derivative in the X direction. And that is equal to my n by n matrix of right-hand sides. So this is just the same system of linear equations. I've just written it down now where the unknown is a matrix instead of a vector. So how do I solve this with the FFT? Here's the three-line solution. I'm going to do the two-dimensional FFT on my matrix of unknowns. So B is a two-dimensional matrix. I'll do the 2D FFT. What does that mean? That means I'm going to multiply B by F on this side and F inverse, F transpose on that side. And I'll get a new matrix B prime. So there's a big chunk of the cost. There's n squared log n. So what happens now when I substitute that into my equation? I claim my equation becomes diagonal, and it becomes very easy to solve. So what I'm going to do is I'm going to take my original equation, L1x, this one got here. I'm going to substitute L1 equals FDF transpose in there. So I get FDF transpose times X, and there's X times FDF transpose, and that equals B, where B is FB prime F. So now I factor out an F on the left, I factor out an F transpose on the right, and I'm left with a diagonal matrix times a matrix of unknowns plus matrix of unknowns times diagonal equals my two-dimensional Fourier transform. So this gray shaded region is just the math, it's not the algorithm. The only algorithm part is a two-dimensional FFT, and that gives me a system of equations that's now diagonal. That's easy to solve. Here it is again. So how do I solve it? I just take each entry of B prime, divide it by the right diagonal entry, and I get an entry of X prime. So that's a bunch of divisions. And so now I have X prime, and I do a two-dimensional FFT backwards to get X back. So I go from X prime to X. And so the steps, so just ignore the gray now. I do a two-dimensional FFT, I do n squared divisions, and I do another two-dimensional FFT. And so the total cost is n squared log n for my n, because I'm doing that many FFTs. Okay? And 3D Poisson would be analogous. I would do three-dimensional FFTs, do a lot of divisions, and then another three-dimensional inverse to get the right answer. And that justifies, so are there any questions about this algorithm? Because that justifies this line on this table, which I've shown you many times. I think we've now gotten to the last line in this table that we'll see this semester. Here's the FFT. It runs in n log n time. The lower bound is n, so it's pretty close. And if I had a perfect parallel machine where communication was free and I had n processors, I could do it all in log n time. And I'll show you that later. But of course, we'll have a real algorithm too, where we try to minimize communication. So that example was I was multiplying not by the exact FFT, I was just multiplying by the imaginary part. And depending on the application, people will do a lot of very similar things. To keep this lecture simple, I'm just going to do the complex case where I want to multiply by this matrix, each of whose entries is omega to the j-kth power. I've written it out there explicitly. And the nice thing, I said this already, is that this matrix, I have to multiply by its inverse too for all the applications. It's basically the same idea, because the inverse is just the complex conjugate. And multiplying, if I can multiply by f, I can multiply by its complex conjugate very fast, and there's some scaling too. And so for Poisson and other examples, I sometimes just multiply by the imaginary part. If I'm doing JPEG, I just need the real part. But if I have a fast algorithm for the whole thing, you can imagine the algorithms for the real and the imaginary parts are pretty simple. Okay, so now let me derive the algorithm. How does the FFT work in n log n time? And so here it is on one slide. I'm going to convert the FFT and recognize that I'm really just evaluating a polynomial at a whole bunch of different points. And then I will come up with a divide and conquer way to evaluate that polynomial very quickly. So here is f times v, and I'm going to take the jth entry and let me just multiply it out. It's the dot product of the jth row of f and my input vector. I'll plug in the definition of what f sub jk is. It's the root of unity to the j-kth power. And now I'm just going to insert parentheses and notice that this looks like a polynomial. The coefficients of the polynomial are the v's. And I'm evaluating it at the point omega to the jth power. And because there's the exponent k, and I'm multiplying it by the kth component. So let me define this polynomial capital V. Its coefficients are the vk's, and it's just a regular old polynomial. And I need to evaluate it at omega to the 0, omega to the 1, omega to the 2. I have to evaluate this polynomial at m different points that are very closely related. They're all just different roots of unity. So what I need to do now is figure out how to take this problem. This is a problem of size m, and break it into two problems of size m over 2. And then I can be recursive and go really fast. So what I need to do is figure out how to take this problem, which is evaluating a polynomial. The degree of the polynomial is m minus 1. There are m terms in it. I'm evaluating it at m points, so that's the problem of size m. And I want to make it two problems of size m over 2. And the idea is this. Here's my polynomial again. I've just written it down. I'm just going to take the even-numbered entries and the odd-numbered entries. So this is the 0th, v0, v2, v4, v6. I take all the even ones, and they're going to get multiplied by x to an even power, x squared, x to the 4th, x to the 6th, and they're the odd ones. The odd ones all have a common factor of x, so let me just pull that out. So I have an x times v1, and x cubed times v3, and x to the 5th times v5. Let me pull out the common factor of x. And now what I notice is that this is a polynomial, and it has half as many terms in it. And it's a polynomial that I'm evaluating at x squared, right? Because there's x squared, x to the 4th, x to the 6th. So let me just define that to be a polynomial of half as many terms evaluated at x squared. And this also has half as many terms. I'll call that v odd, because it has the odd components, v even for the evens. And so I'm sort of partway there. I want to evaluate this polynomial at m different points. I want to break that down into evaluating polynomials with of half the degree, two of them, there they are. And I'm almost there, except I want to evaluate it at m points, and it looks like I have to evaluate this at m points, right? That's not half size yet. So here's the trick. What I notice is that when I square all these numbers, when I square all these roots of unity, then half of them go away, because they come in plus minus pairs. And so when I square them, I only have half as many as I had before. So here's the algebra, if you like. I have all these roots of unity. So omega 1, omega 2, omega j. So the question is, what happens if I take omega j and the one that's a little bit farther along, halfway farther in the list, j plus m over 2, and I square them? I pull out, this is the laws of exponents, I get omega to the m. Omega to the m is 1, because omega is the mth root of unity, and so these are the same. So I only need to evaluate these two polynomials at half as many points. So now that's my divide and conquer. This is a problem of size m, and here are two problems of size m over 2. So now the whole algorithm fits on one slide. Here's the divide and conquer FFT that runs in time m log m. And so I'm going to pass in my vector of unknowns. I'll pass in my root of unity just to remind me what it is. I'll pass in the dimension. And if I'm at the bottom of my recursion, if it's a 1-by-1 problem, there's no work at all. I just return the answer. It's just a constant. Otherwise, I take the even-numbered components of V. So this is MATLAB notation for V0, V2, V4. I evaluate it at the point x squared, so omega squared, and at half its length. I do the same thing for the odd. So they're my two calls. I need now to evaluate it at all these different points. So they're all my x's. So they're all the different values of x there. Let me just write them all out as a vector. And now in MATLAB notation, I take the evens plus the odds, and I multiply it by all the different values of x. So this is a vector. That's a vector. This is MATLAB notation for multiply component by component, and add it to the evens. And the other ones, the only difference between these values and those values is a change of sign, because they come in plus minus pairs. So there's a plus and a minus. And otherwise, I don't have to redo these multiplications. And so this is the whole algorithm. It gives you the right answer. And what's the complexity? Let me let t of m be the time to call this. Where's all the work? Well, there's one call, t of m over 2. I have two of them, so it's t times m over 2. And then this is order m multiplies and order m addition, so that's order m, solve the recurrence, and it's order m log m. And of course, I don't need to recompute these every time. They're going to be pre-computed, sitting in a table. They're just available. So this is the algorithm that has been known for a long time and has an interesting history of how it got published. which I'll come to, which I'll tell at the end of the lecture, I think, if there's time left. So let me now try to describe how we're going to parallelize this. Yes, question, microphone. I think so.
Better?
Let's try it.
Okay, let's try it. All right. So I think we're understanding the reason for why we do the split all the odds in one place and evens in the other. Like, would it work equally well to just split 0 through n over 2 in one side and n over 2 through n?
No, because then we wouldn't be able to use this trick of evaluating it at half as many points. By doing the evens and the odds, we also only get half as many points at which we can do the evaluation. But you may ask, what happens if I don't have, an even number of components, right? So to continue to be able to do this divide and conquer, I'm going to assume that m is a power of 2, so I can keep dividing in half every time. But people want to do FFTs on things that are not powers of 2, and in fact, FFTW and Spiral have a whole host of different algorithms that work on arbitrary integers. But I'm giving you the simplest case where it's division by 2. Okay.
Mm-hmm. So I don't hear people talk about FFTs a lot. I don't entirely understand what their output gives you. Like, why do you zero out the 2.5?
So what I've done, let me go back to the picture here. So if I do the FFT, so this is my signal V. This is F times V. So that means this is, if I can write it as F transpose times this, the inverse. So F transpose is just a vector of sine curves. So what I've done is expressing this as a sum of sine curves. What are the components? How much do I multiply each sine curve by? It's the value of the FFT. So the FFT has done a Fourier analysis. It's re-expressed my input as a sum of sine curves of different frequencies. And which frequencies appear? Well, it's 5 and 7, which I can see from that plot. And so it's re-expressing signals as sums of sine curves. So yes, the resolution depends on how many points you have, and so I'm never going to see more than 64 different frequencies if I only have 128 points. So people obviously like to do much, much bigger arrays than this, but this picture works fine too. Any other questions? Okay. Okay, so what I'm going to do now is take this divide and conquer algorithm and write out every last detail for the case of m equals 16, and that's going to let us know, we're going to look at that and see a pattern, and it'll tell us how to parallelize it. So here is the complete call tree of the algorithm I just showed you. I'm going to call the FFT, I'm going to input a vector of length 16. It's going to be, and what are the subscripts? It's going to be passed in V0, V1, V2, up to V15. 16 is a 4-bit number, so I can say that what I'm essentially doing is I'm passing in all numbers that can be written down with 4 bits, x, 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 x. Each of those can be either a 0 or a 1. That gives me these 16 different numbers. Now, what does the divide and conquer do? It says I take the even-numbered values and I take the odd-numbered values. That's the first recursive call. How do I decide if a binary number is even? Well, the last bit is 0. So all I've done is I've taken these 16 numbers of 4 bits, and I say the last bit has to be 0. That's what's passed down to this side. And so I get 0, 2, 4, 8, up to 16. The odd ones are where the bottom bit is a 1. And so this is what all of their binary expansions have to look like. Bit, 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 1, 1, 3, 5, 7. And that's what gets passed down to that side. I do it again. So now this is, in the next recursive call, I take all these numbers, and I want to take the even-numbered ones of those. How do I tell which are the even-numbered ones of those? These 8 numbers, I look at their expansion, and again, the bottom bit has to be 0. So here, if I take even and then even again, I'm looking at all the numbers whose bottom 2 bits are 0. If I pick odd and then odd again, the bottom 2 bits have to be 1. So at each step in the recursion, what I'm basically doing is fixing the next bit in my number, and I'm going to assume that all my numbers are binary numbers. Until finally, at the bottom, if I've chosen all even, I get zeros. If I've chosen all odds, I get 1. And then I get all these different other expansions in between. And so at the very last step, what do I do at the very last step? I've chosen these 3 bits to be all the same. They're all zeros. And the first bit is either a 0 or a 1. And so what happens this is where we finally do the arithmetic. I'm going to take the numbers whose values are 0 and 8, combine them with some linear combinations, 4 and 12, 2 and 10, and so forth. And this is the output of the algorithm. So do you see that these numbers are not in the same order as the inputs, right? The inputs are in the order 0, 1, 2, 3 in sorted order. Now, when I run this, the outputs are going to come out in the order 0, 8, 4, 12. So can you see what the order is that these are coming out of the algorithm? I mean, they're not in sorted order, but they're in almost a sorted order. And it's in red. There's a red hint on the slide. Yes, it's bit reversed order. So if I look at these, I have 0, all zeros, and then 1, 0, 0, 0, and then 0, 1, 0, 0, and then 1, 1, 0, 0. If I look at the bits backwards, these are in order. And that is what is the output of the algorithm. And that is going to have to be taken into account when we show you what the parallel algorithm does and who has to communicate with whom. So what I'm going to do on the next slide is to show you, again, a complete breakdown of the entire algorithm, every last multiply and divide, and just look and see what the pattern is. So here are the 16 numbers that I input, and their bits go from all zeros to all ones. And after at the very first multiply and add that I do is going to give me this next layer of 16 numbers. That's after they've gone through one step. Then I'll do another multiply add. I get another 16 numbers. And finally, this is the output. So what I've done here is drawn all the patterns. So let's go back to here. This says that at this point, you need to take the number whose bit pattern is all zeros, combine it with a number whose bit pattern is 1, followed by all zeros. That's what I've drawn here. All zeros, 1, 0, 0. And this butterfly shape, and this is called the butterfly algorithm, indicates that I'm going to take a linear combination. This guy here is going to be a linear combination of the 0th and the 8th. And this guy will also be a linear combination of the 0th and 8th. And they differ only in if they're doing add or subtract. They're doing the same multiplies. And then at the next layer, I'm also going to do another butterfly. But now they're only differing in the second bit. So this is 0, 0, all zeros, and 0, 1, 0, 0. That's differing in the next bit. So that's the next combination. And at each layer, the distance, the length, the wingspan of the butterfly is going to be depend on which bit it is. So here, the wingspan is 8. And so this butterfly is of that length. At the same layer, if you look at the next one, it's a little hard to see, there's a red butterfly. It's going from 1 down to 9. Here's the next butterfly going from 2 down to 10. All of those get combined. At this layer, the distance is 4. The distance is half as big, then half as big, then half as big again. And so this represents every last communication in the algorithm. And so let's suppose now, and now I need to parallelize this. I sort of see this picture, and you can imagine what it looks like for arbitrary n. I need to assign work to processors, and I need to make it run as fast as possible by minimizing communication. So if I had n processors, then and communication were free, then each of these layers could be done in constant time, right? Each processor would grab the two numbers it needs and multiply and add, and so it would take me exactly log m steps to process each column. But now what I really have to do is assign this to data. So let's remember our linear algebra lecture. There were two ways to assign a matrix to a bunch of processors. And one was blocked, and the other was cyclic. I'm going to use exactly the same ideas here. So what were those two different patterns? If I have 4 processors, I could say the first processor gets the first 4 entries to work on, the next processor gets the next 4, next 4, next 4. Okay? That's the blocked algorithm. What was the cyclic one? I deal these out like a deck of cards. So processors 0, 1, 2, 3 gets those, then 0, 1, 2, 3, 0, 1, 2, 3. That's the other obvious way to do it. Let me just try them both and see what happens. See which assignment of work makes sense. So here, let me try the blocked one. And I've color-coded it by 4 different processors, numbered from 0 through 3 and colored. And so what I've done is indicated which entries of the intermediate results each processor is responsible for. So the green processor is responsible for doing all that work, the blue for all that, and so forth. And what I've done is left in all these lines that indicate who depends on whom, but if the green processor's data is all local, I've colored it green. So here, to compute that, the green processor needs that number and that number to follow those edges. He owns them both, so I've colored all those edges green. But over here, to compute that guy, the green processor owns one of them, but he has to go down, he owns that one, but he has to go down all the way to the red processor to get the other one. So that line is colored black because there's communication. So it's clear that this blocking does a good job. There's no communication at all in the last log m over p steps. But in the first log p steps, then everybody's communicating with everybody. So I've solved the problem there, but here there's tons of communication. Yes, question?
So I was wondering, how come you don't do this graph where things are in order, like bit reversed order or something? And
Well,
then shouldn't it be like a binary tree in that case?
Well, at the end, the answers, if you ask in what order do the answers come out at the end, I put them in regular order. They come out in bit reversed order. So this is, these are the numbers that appear at the bottom of this tree in that bit reversed order. But I'm showing it to you in sort of the simplest way to draw the tree here with these butterfly patterns. So the green processor will own 4 consecutive answers. They will not be 0, 1, 2, 3. They're going to be 4. They're going to be consecutive answers in the bit reversed order.
Well, so I was just wondering what that graph would look like if the numbers are ordered in bit reversed order.
Well, these are in bit reversed order. Maybe the next slide will answer your question. Let me just try the next slide. So this is what happens if I do the obvious blocked assignment of work. The other one was cyclic, so let me try that one and see who communicates with whom. So here's the cyclic ordering. So now the green processor owns every fourth, the blue processor owns every fourth. And now there's no communication at the beginning, right? Now when processor 0 needs to get the 0 and 8, he owns them both, and so those lines are both green and there's no communication. That's true for the first log m over p steps. And then at the end, it's black. That means there is communication at the end because now this processor has to go, the green one has to go to get him. He owns 1, but he has to go to the red processor to get that number. So it's exactly the opposite of the picture as before. Now I have no communication here, and I have all the communication at the end. So what I would like is the best of both worlds, obviously. I would like to have no communication here and no communication there. How do I do that? But before I do that, let me just write down the complexity of both of these algorithms and so to give us a hint of where we are now. So I'm going to write down one formula for the number of words moved and the number of messages, both for this layout and for the layout I just did. And so the answer is going to depend on, of course, the vector size, the number of processors. I'll assume the time per flop is 1. I'm just going to confirm that the load balance is perfect. The latency, I count the number of messages. Time per message is alpha. And then beta is the reciprocal bandwidth. And so it turns out these run in exactly the same amount of time. And the flops are perfectly parallel, 2m log m flops divided by p. There's going to be one message at each stage, at each black stage. How many black stages are there? Log p. So there's going to be log p messages. And then this is the bandwidth cost. And so how big is that? Again, let me look at this picture. Every processor has to move everything it owns somewhere else. So how much does it own? It owns m over p. And so it's going to do m over p, and it's going to do that log p times. So there is the bandwidth cost. And I would like to do better than that if possible. And so let me show you the final algorithm, which is to some extent the best of both worlds. I'm going to change data structures in the middle of the algorithm. So I'm going to start with a cyclic layout, and I'm going to have no communication at the beginning for the first log m over p steps. And then I'm going to transpose all the data. I'll say why it's transposed in a moment. I'm going to switch from the cyclic layout to the block layout, and then there's no communication again. Okay? So I'm going to put all the communication here in the middle. Now, this example works out really in a nice, pretty way because p is the square root of m in this case. 4 is the square root of 16. And everything I'm telling you is true no matter what m and p are, as long as they're powers of 2. But the picture might have more phases in it if p were not exactly equal to the square root. But let me just not worry about that issue and just deal with this particular example. So you can see that communication is free, communication is free. All I have to do is count the communication to get from cyclic to blocked, and I'll do that. But let me try to say why this is called a transpose. And so let me just draw the two data structures, cyclic and blocked, in a way that makes it obvious that it's a transpose. So here's the block layout. The green processor gets the first 4, the blue processor gets the next 4, and I've numbered them all. And here's the cyclic layout. The first processor gets every fourth, the blue processor gets every fourth starting with 1. And if you look at these matrices of indices, they're exactly the transposes of one another, right? So that row is, that column is equal to that row. And so this is why we've seen this problem before. How do you do a transpose? Because this is, well, the next question. So let me talk about how much it costs to do that transpose in the middle. And I'm going to do a pessimistic assumption, which we'll explore later, especially in the 3D case. We're going to do a lot of pipelining to get this thing to go fast. But if I don't, here's the time for the transpose FFT. The flops are perfectly parallel as before. The number of messages goes up a lot because every processor at this transpose step has to send some of its data to some other processor. So that means everybody is communicating with everybody else. That's p minus 1 messages. That went up from log p. But now the good news is the bandwidth has gone down. The bandwidth has gone down by a factor of roughly log p. And it turns out that hits a lower bound. We're not going to be able to communicate less than this. So this is roughly m over p times the reciprocal bandwidth. And it's a factor of log p less than this, roughly. And this is, as I said, close to a lower bound. So I have to worry about, getting, the latency can be bad. I need to somehow be more clever about overlapping stuff, doing that in parallel, but the bandwidth is as good as it's going to get. So now let me just say a few words about what are the lower bounds that are known about this. So let me just tell you what the sequential communication complexity is. So the question is, how much data do I have to move between fast memory of size capital M and slow memory, DRAM, to do an FFT of size little m? And we've asked this question before for linear algebra. I'll ask the same question now for FFTs. And the answer, it actually goes back to the same paper, is that no matter how I organize all the multiplies and adds, the lower bound is the number of flops divided by now the logarithm of the cache size. Now this is similar to linear algebra. The numerator was the number of floating point operations, which was m cubed, little m cubed. But the denominator was a lot bigger. It was the square root of the cache size. Now it's only the logarithm. And the proof follows because if you look at the FFT, how many times do I reuse each piece of data? It's only participating in log m multiplies. So I just really can't reuse the data very much. And so, but this is what I want to attain. And I claim that that algorithm I just showed you with the transpose actually will attain this lower bound for a sequential implementation. And how would the sequential implementation work? Because I started with a parallel one. It's just going to simulate the parallel implementation. It's going to your algorithm is going to pretend I'm a processor. My memory size is capital M, and I'm going to pretend that there are little m over capital M processors, and I will do step by step what each processor does. So that means the sequential algorithm will do whatever the green processor does, do all of its steps, then do the blue processor, then be the red, then be the brown, then be the green, then be the blue, then be the red, then be the brown. And that will hit the lower bound. And it follows because the parallel algorithm is hitting the lower bound. Now, it turns out that FFTW and the autotuners don't quite work that way because it would be painful to write this code. This is analogous to the explicit blocking you did in the first assignment where you figured out in matrix multiply what size blocks do I use to minimize cache misses. And then we said, well, there's a different way to do it. You can write a recursive algorithm. Just do divide and conquer. And if you do the divide and conquer in the right order, then that cache oblivious algorithm will also minimize the amount of data of memory traffic. And so if you do the FFT recursively and you process this graph, let me go back to it, and you do all of so this is a recursive algorithm. If you process all of these recursive steps in the right order, you will also minimize the complexity, minimize the memory traffic. And so that is what FFTW does, and that's sort of the fastest way people do it now. They do not do explicit blocking. They do it in a recursive cache oblivious way. Okay, so that's, let me just say a little bit about, finish up about the one-dimensional FFT, because I want to go into the higher dimensional case, because that's where people have spent most of their time optimizing. So the above algorithm does leave all its data in this bit reversed order, and that may seem painful. But the good news is that most algorithms, they do two FFTs. They do this one, then they do some filtering, as I showed you. Then they do the inverse FFT. And if you reverse the order of the bits twice, you get the answer back in the right order, right? So you don't have to transpose twice. You don't have to undo the bit reversed order because the algorithm does it for you. Now there's another parallel FFT algorithm that's been invented that I just want to mention briefly. It is not, let's say today, a practical algorithm, but it could be practical in the future. And it uses the fast multipole method. And so let me just, and it's an approximation, it's not an exact FFT. So the analogy is you can think of the FFT as having a whole bunch of points, particles with gravity. The particles are uniformly spaced in the unit circle. And you can ask, if two particles are far away on the unit circle, in the sense of arc length, then can I approximate the particles that are far away in some cheap way? That is what this Edelman's algorithm does. And it does significantly less communication, but it only gives you an approximation. But it does so many more floating point operations, it's not a practical thing yet, but it could be in some future date. So this is an interesting mathematical algorithm. Okay. So let me now talk about higher dimensional FFTs. And as I mentioned before, the basic idea, if I have a two-dimensional case, I'm just going to do an FFT to all the columns independently, and then do an FFT to all the rows. I could do that in either order because it's associative. So the question is, what are the obvious ways to do it? I mean, I have a building block now, a sequential FFT. So the simplest thing to do, this is the first one, is I have a two-dimensional layout. So I break up my matrix into blocks, a square root of p by square root of p processor grid. And then each column is owned by square root of p processors, and I just do 1D parallel FFTs for each row in each column. That's one possibility. Another one is that I'm going to do a block row layout. So each processor owns n over p rows. And then if I start by doing row FFTs, they're all local to one processor. It's all serial, and so they all run embarrassingly parallel. They do the row FFTs. Then I transpose the entire matrix, so each processor owns a block of columns, and again, I do serial one-dimensional FFTs. And the last possibility is I start with a row layout again. I start with independent row FFTs, embarrassingly parallel, and then I do parallel FFTs in the columns because they are owned by P processors. It's going to turn out that they're all balance the flops perfectly well, but option 2 is going to minimize the communication for us. So we're going to do local FFTs, transpose, and then do local FFTs again. Now, it turns out that 3D is what people are most interested in, and the design space gets very interesting there. And so I'm going to sort of dive a little bit deeper into how a three-dimensional FFT works. And for that, I need to tell you a little bit more about the hardware, because the options that people have explored for this depend very much on how you can overlap communication and computation. So I need to look at what the hardware networks look like in a little bit more detail. So no matter how I do it, I'm going to have a transpose in there. So every processor is going to be sending an equal fraction of its data to every other processor. And if I wanted my hardware to do that perfectly, it would just, it would be so expensive, nobody builds that kind of network. Basically, every processor would have to be directly connected to everybody else. I'd have order p² wires in the machine to have everybody connected with everybody else. That nobody builds machines that way. And so I'm going to be limited by something called the bisection bandwidth, which I mentioned in an older lecture. That tells me if I break up my processors into two groups, the bisection bandwidth is the limit on how much data I can ship from the one half of the machine to the other half of the machine. And since everybody's talking to everybody, I have to do that. I have no choice but to cross that boundary. And so what I'm going to do then is to overlap, because I'm going to be limited by this bisection bandwidth, what I want to do is have parallelism in the sense of overlapping communication and computation. I need to run those at the same time. Otherwise, and so there's a factor of 2 if I can get them to line up perfectly, but if I don't, I will be in trouble. So let me now give you a slightly more detailed model of how the hardware works than simply counting messages and counting words. And this is something called the log P model, or the log GP model for sending large messages. And so I need to sort of explain where the overlap comes from, possible overlap. And so I'm going to show you 2 different models here, both without overlap and with overlap. And so what I'm showing you here is sort of a timeline. The vertical axis is time. Processor 0 is trying to communicate with processor 1. And so this vertical axis tells you what processor 0 is busy doing. This vertical axis tells you what processor 1 is busy doing. And so what processor 0 needs to do is pack up a message. For that period of time, there's some overhead to pack up the message to send it. So he's busy there. Then he's freed up, but now we have the network latency. So this next bit of time, neither processor is busy, but the message is off traversing the network. There's other hardware taking care of it. Finally, it arrives over at processor 1, and then processor 1 is going to be busy for a while. He's going to have some overhead to do the receive, to unpack the data, and put it wherever it belongs in his memory. So the question is, what are the overlap possibilities? For processor 0, he's busy right here, but this time period from there to the arrival, he's sort of free. He could be doing computation during that time while this communication is going on. So there's a potential to save, to overlap, and run in parallel this brown plus this blue over here. So that is some kind of hardware fall into that category. So other kinds of hardware fall under this kind of model instead. So processor 0 can pump many things into the network. So he's busy packing for a while. This green line is the same as OSend. But then he can't immediately start sending another message, say, to a different processor. He has to wait a little while. There's a gap. And then he can start sending again. And so he could send to processor 1, then he could here start sending to a different processor and so forth. And these numbers, G, that's the reciprocal bandwidth, and OSend, these are all hardware parameters. So what is the overlap possible here? It's between there and there. It's this gap from there to there. That's the possible overlap. And so all of these can be measured on different machines. There's interesting benchmarks. But so what I'd like to you understand where the potential overlap comes from. So I can do computation there, or I can do it there. And the question is, which one gives me the most opportunity? So what I'm going to do is I've run some benchmarks on some different machines. And what I'm going to show you is how much time falls into these categories. So here are a whole bunch of different machines. So in fact, and each machine is going to have different memory passing software tools on it. So the innovation is, can you get the software to take advantage of what I just showed you in the previous slide? So this are 3 different ways of using a Cray T3E. These are 2 different ways of using an IBM cluster, a Quadrix network, a MirNet, and then a Gigi network, but running different software layers. So there's MPI, something else called VIPL, and they all come out different. And so what this has done is it's measured the entire time in this picture from there to there, from top to bottom, by running a benchmark. And it's broken it down into the 3 components. The time it takes to do the overhead at the top, to pack it up, to unpack it at the end, and the latency added from the network. So the total message time from top to bottom is the total message time from there down to there. And if I just look at let me get this right, the green plus the yellow, that is, the green plus the yellow is the time from there to there. That's the amount of time for which processor 0 can be doing some useful computation. And so you can see the green plus the yellow adds up to quite a bit on some of these processors, and that's the opportunity we want to take advantage of. So, and this machine doesn't fit this model very well. In this case, the send and the receive are happening at the same time. That's because in this particular implementation of MPI, the 2 processors are handshaking with one another. They're saying, oh, did you get my message? Yes, I got my message. And so they're both busy at the same time. And so this is represented by this cross-hatched region where both the processor 1 and processor 0 are simultaneously too busy to do anything else. But most of the machines give you this opportunity. Okay. So all of this depends on what the hardware looks like, and I don't want to spend too much time on it. You need direct memory access. You need a network interface card. There's some machines where the network interface card gives you what's called remote direct memory access. So when the message arrives, there's no receive overhead. It's put where it belongs in memory. And all of these are taken advantage of by GasNet. So let me move ahead here. So GasNet is the communication layer that underlies UPC. That's what you're using in your homework assignment right now. It lets you do all of this overlapping for you. It's much more flexible than MPI. You can just say, please put a message in the network and have it delivered. And the receiving processor does not have to spend a lot of idle time waiting for it. Or in fact, the network interface card will simply put the data where it belongs because the destination address is transferred with the message. And so there's going to be a lot more opportunity, and in the slides that follow, I'll show you to make the FFT run faster with GasNet versus MPI. So let me show you some more benchmarks. I want to compare how long it takes to send messages using the GasNet as opposed to using MPI. And so here is a plot of sending a very large chunk of messages broken up into chunks of various sizes. This is a log scale, so into 10 byte sizes, 100 byte sizes, 1,000 byte sizes, up to huge messages. And the vertical axis is the bandwidth that's gotten, so up is good. And the blue is GasNet, and the red is MPI. And so up here, where I'm sending very, very large a few very, very large messages, these are both limited by the hardware bandwidth, and they're both peaking out at around 80 megabytes per second on this older machine. And so if you send large enough messages, there's not a big difference between the two. What's better is if you send lots of little small messages. So let's suppose that I send messages of size around 10,000. So I'm still getting nearly peak speed out of GasNet. So I'm still getting nearly the peak. I don't get much of a drop there, but MPI has dropped dramatically. So this says that if I send lots of messages of size 10K instead of 100K, then that's going to give me lots more of those little latency pieces that I can overlap, and it's going to go a lot faster than MPI. And so and this is the speed up difference there. There's like a factor of 2 difference between there and there, for example, where there's a benefit from using GasNet. So let me show you some other measurements here. This is what fraction of the peak bandwidth I can get using MPI versus GasNet on a whole bunch of different platforms. Sometimes it's the same platform, but with different networks. And the vertical axis is the percentage of peak. And so this is what fraction of the total bandwidth I can get if I'm sending little 4K messages. And you can see that GasNet gets a much larger fraction of them than MPI does. Okay, so what I'm going to do now is take advantage of this fact that GasNet will let me send lots of small messages about as fast as the full bandwidth of the machine to do more overlap. And I'm going to use that to optimize 3-dimensional FFTs. So it turns out that just like for matrix multiply, people have contests to see who can do the fastest, solving AX equal B. There's also contests for doing the Fourier transform. And so, in fact, there's a published benchmark. These are the NAS FT benchmark is a case study. These are the NASA Fourier transform benchmark. And so what I'm going to do is show you what it looks like and optimize it both, show you what the design space looks like, and then optimize it using GasNet and compare it to FFT. And what this benchmark does is it lets you download a version that somebody else has optimized. It's written in Fortran, and it calls MPI. And I'll also show you how much faster it can go than that particular implementation. This project started as a class project in 267 a number of years ago, and for a while it was the fastest FFT. So here is the 3-dimensional picture of how the 3-dimensional FFT works. So I have this 3-dimensional brick of data. So it's nx by ny by nz, and I want to do an FFT in every direction. So I want to do an nx-sized FFT, and how many of them are there? They're going to be nz times ny of them. And I want to do that in all 3 dimensions. And so the question is, what is the best layout? And so let's suppose I have 4 processors. If I want to minimize communication in the first 2 FFTs, then here's the obvious best layout. So each processor is going to own a quarter. It's going to own what I call a slab. So this is a slab here. And so this tells me that since this processor owns all these, everything in that direction, everything in that direction, it can do all of the vertical one-dimensional FFTs with no communication. Then it can do all the, that's the x direction. Then it can do all the y direction FFTs with no communication. And everybody can do that in parallel, no communication. I finished 2/3 of the work. But now, to do the FFT in the, going into the board direction, in the NZ direction, I now have to do the communication. The question is, how do I optimize that particular step? Okay, so let me show you how this might work. So, all right, I've already said this in words. So I'm going to do the FFT in the x direction, then I'll do it in the y direction, and then finally I need to do it in this direction. So the question is, how do I parallelize that? And so what I need to do somehow is get into this layout at the end. I need to take all of these guys and transfer it into this direction so that now in the z direction they're all local FFTs. So the question is, how do I get from there to there in the fastest possible way? And here's going to be the design space. So there are going to be 3 different sort of granularities. The easiest thing that you can imagine is that, going back to this picture, this guy takes everything that he owns in that big brick up here, and he's going to send it to all the other processors. So it's going to be sent, so aimed that way. So this brick will go that way. It'll end up in the red. He's going to send as few large messages as possible. I'm going to call that packed slabs. So I'm going to minimize the number of messages. Each message is going to be as big as possible, one to each other processor. Then I'm going to also look at the possibility of sending a smaller piece, but more of them. That'll give me more opportunities for overlap. And then the third possibility is I do a very, very tiny bit of work and then immediately start sending that to the next processor. As soon as I finish a one-dimensional FFT, that's called a pencil, one-dimensional piece, I will start sending it to everybody who needs that data for the final z-dimensional FFT. Okay, so let me just show you what the picture looks like, and I'll show you all the details here for a 16 by 16 by 16 FFT with 4 processors. And so if I look at what does one processor own, here's a 16-dimensional slice. It owns 4 of them. And so it's going to begin by doing all of the row FFTs, and there are 64 of them. It can do those all locally. Then it can do all the columns. There's 64 of those. And then what it's going to do is pack up and send to the neighbors what they need to do. So what does it need? So it's going to keep all of the green parts. It's going to take all of the orange parts, pack them into one message, and send them to the orange processor. It's going to take all the yellow parts, pack them into one message, and send them to the yellow processor, and the same for the blue. And so it's going to send exactly 3 messages. It's going to keep the green stuff. All the orange will get packed into one message going to that processor, one message there, and one message there. So, and then those get sent to the destinations. So it doesn't actually have to send it to itself. Let me just put it that way. So let me do the counting. So let's suppose that I did instead of a 16 by 16 by 16, let me make it a little bigger, 512 by 512 by 512. And let's suppose I had 64 processors. Then I'd be sending 64 of these messages, and each message would be 512 kilobytes. Okay, so that's sort of the fewest messages, but they're all as big as possible. And that is how the NAS parallel benchmark works. And the trouble is, it's only getting 67% of peak bandwidth if you do it that way. So there's all sorts, so we're only getting 67% of the bandwidth. Could we do a lot better? That's what the other optimizations are going to do for me. So here's the second one, which is called Slabs. And what I'm going to do is I still have to send the same data to the same places, but let me break it up into smaller pieces. And so I'm going to start by doing all of the column FFTs. So each processor in my picture here is going to own 4 of these. Let me just look at the first one. So I'm going to finish all the columns. Then I'm going to begin working on the rows. And each of these guys is called a slab. And so what I'm going to do is, I've finished all the columns. As soon as I finish this particular slab of green stuff, I can pack it up and start sending it to processors to 0 where it belongs. And then while that communication is going on, I can immediately start doing all the FFTs of this slab. And as soon as I'm done, I'll send it to processor 1. And so this communication is going to go on in parallel with all of the FFTs of the yellow part. So there's the overlap there. Well, that's going to processor 2. And then finally, this is overlap with all the FFTs of that. And well, that's going to processor 3. And that is going to be overlap with the next plane, remember, because I own 4 of these things. So I'm going to be able to overlap, potentially, all of these different slabs with everybody else. And so if I count messages and bandwidths and all of that, for a much bigger grid, 512 cubed, 64 processors, I'm going to be sending the same amount of data, but now it's going to be 512 messages instead of, so on the previous slide, I had 64 messages of size 512K. And now I'm going to have 512 messages of size 64K. So same total volume, but this is going to give me potentially more overlap. And so pencils is a very similar idea. Again, here I'm going to start by doing all of the column FFTs. I'm going to finish all of those. And then here's where the destinations are. And so I'm going to start by doing just one FFT. And as soon as I'm done with that, I'm going to send it to processor 0. And while that's going on, I will immediately start doing the FFT not of the next guy, but of that particular row, because he's going to be sent to processor 1. So while that communication is going on to processor 1, I can do the next FFT there, send that to 2. That communication, again, will overlap with that. And then that will overlap with that. So in the inner loop, I'm sending to different processors. So processor 0 gets a little message, then 1 gets a little message, then 2, then 3, then back to processor 0. So if I were to send them all to processor 0, then there'd be network contention. If I just went by consecutive rows and kept shipping them to processor 0, then the network between me and processor 0 would be so busy, it wouldn't work. So this way, I'm sort of spreading out all the work over all the network. And I just keep going and going until I cycle through the whole thing and get to the next plane. And so every little message is going to go to a different processor. And there's a question.
So how about randomly choose the order?
So the question is, how do I decide the right order to make sure everything gets there at the right time? So I have to make sure that eventually everything is sent. If I did it in a randomized order, that would rather complicate the bookkeeping, I think.
So the problem is if we assume that every processor execute at the same speed. So if you calculate, processor for the processor 0 and send the message, and for the second processor is also sending the message during that time to processor 0.
Right. So
there will be
right.
boost.
So this is very much designed for a machine where everything is homogeneous, and we're assuming that the network is only owned by us and nobody else is doing anything with it. So we don't have to worry about randomization to take into account that there might be something busy somewhere. So your algorithm might be better if I have a shared resource or one that's so big, future ones will be so big, that there's going to be some random behavior simply because some of the machine's up, some of the machine's down at different times. But this was definitely optimized for the nicest possible case where you control everything, it's all yours, everybody's running at exactly the same speed. And since this is a benchmark contest, that's the kind of machines people run on. And so here, now I'm sending lots and lots of messages, and they're, again, smaller by a factor of 8. So let's ask ourselves, let me start showing you some benchmarks to see how much benefit we get from it. And so what I'm going to do first is show you not the algorithm itself, but just let's look at the time it takes to send messages of this size and ask ourselves which of these size, the biggest, fewest messages or the most small messages, gives us the biggest potential for speed up. And so the way I'm going to do that is by looking just at the bandwidth that I can get out of this machine for sending byte messages of different sizes, ranging from 16-byte messages up to really, really big ones, 256K. And so the vertical axis is bandwidth, up is good. And I'm going to be comparing GasNet versus MPI. And so if I'm sending lots and lots of large messages that are of size 512K, then this is where I'm going to be running. I'm going to be running at the peak speed, and MPI and GasNet are going to be about the same. So I don't expect to see any difference between them. So let me go now to Slabs. They're going to be 64K messages. So let me look here. And again, I don't see a whole big difference. It'll be a slightly better if I use GasNet and get that overlap. But now if I look here, GasNet is almost giving me the peak speed, and it's going to be going a whole lot faster than MPI. So this size problem, I kind of expect to have the most opportunity for overlap by sending lots of small messages. Okay. So let me now, so this tells me that I'm going to expect this benefit. I'm going to run this data on a lot of machines, and I'm just showing you this for the sake of reproducible science. It was run on an Opteron cluster with InfiniBand and an Alpha cluster with an Elan network. And it's a little bit of a joke to say reproducible science because many of these platforms don't exist anymore. But at least it's well recorded. So we could, in principle, reproduce the data. So let me show you the comparisons in speed. And what I'm going to do is on all of these different platforms, I'm going to tell you how fast they are relative to the speed of the version that was downloaded that's written in Fortran and calls and uses MPI. That's speed 1. And so up is good. And so all of these are running a multiple of that speed. That's a good thing. And if you, let me look at these labels correctly. So these are all the different UPC versions using the different size messages. So this is pack slab, the fewest large messages. Green is slabs, so more smaller messages. And finally, the orange is where I send the tiny little pencils, so the most tiny messages. And you can see it's monotonically better idea to send more smaller messages because of the overlap of the computation and the communication. And so on all of these, you can get a speed up, and there's like a factor of 1.9 speed up in the best case versus the MPI code by doing this kind of overlap. So the natural question to ask is what part of the time is spent in communication versus computation? So here's a slide that just breaks down the communication time. And so again, this is showing UPC versus MPI now. And so slabs versus pencils. So pencils, again, being the most tiny messages, slabs being in the middle. And so now down is good because the vertical axis is time. And the first two colored bars are UPC. The next two colored bars are MPI. So UPC always wins, sometimes by a very large margin. In fact, there is no bar here for MPI with pencils because MPI kept crashing. It couldn't handle all the little tiny messages. And so you can see that there's a significant improvement in the communication time. And so we didn't always see speedups this big in the previous slide. That's because both machines are doing arithmetic. They're both running FFTW to do the local FFTs. So those are running at about the same speed. So that amortizes how much benefit you get here from the communication. But this could be your energy improvement, right? If you spend most of the energy going into communication. And so you can see there's a very large improvement going from there to there, for example. And so finally, here's a performance summary, which says here is the best speed. So here, vertical axis is megaflop, so up is good, going from the best MPI version to the best, so for the best Fortran MPI, for the best MPI with slabs, that's running it in C with a new algorithm, and then the best UPC version, and that was always best to use pencils. And so you can see that it always wins, to send the most small messages. Question?
So I just want to check. The MPI versus UPC isn't actually the important part here. The important part was the message size and the GasNet versus MPI. I just want to check that. Is that true?
So there's MPI versus UPC is important because UPC gives you, the way it's implemented lets you overlap more. Because it implements the log P model, which exposes the opportunity to overlap communication and computation better than MPI does. And the other important thing is that given that opportunity, you want to take advantage of it by sending more small messages. So I guess there's sort of two messages there. Okay. So let me just show you a little bit more data. So this is a study on IBM Blue Gene P. Here the improvement was not nearly as significant, and it was only like about 17% by going from packed slabs to slabs, but it was still a good thing to do on that particular platform. And finally, some data on Franklin, which was the predecessor to Hopper. And here the story is similar. So UPC with slabs is the green bar, and again, it's almost always winning. Except for this particular machine, it turns out that they optimized MPI to send small messages. And so if you're sending a very small problem, the horizontal axis is the problem size. So this is a small problem. Here, MPI actually won because of the way they happen to optimize MPI in this particular machine. So the story does change from platform to platform. So that's all I wanted to say about optimizing the 3D FFT, to give you a sense that there's a complicated design space and to show you it depends on the hardware in a significant way. And if there are no questions about that, I want to say a little bit about the auto-tuning, because this is something that people have worked on very hard to try to auto-tune it. So I'm going to use the slides that are provided by the folks who built FFTW, the fastest Fourier transform in the West. It will it will let you say which version of the FFT do you want, because there's a complex version, the sine transform, the cosine transform. It'll say what value of n do you want it to run on. It doesn't have to be a power of 2. You can say I want it for any number you like. Could be a prime number. It'll still do a very good job there. What architecture do you want to run it on? And it will hand you a very, very good sequential implementation, and I'll show you data that they sort of beat everybody else. Now, there are two competing projects in this domain. There's another one called Spiral, which is now a startup. But an FFTW is sort of publicly available. So I'm not going to say that one is better than the other. They're both very good projects. This is very similar in spirit to some of the auto-tuners I've talked about earlier in the semester. I talked about Atlas for tuning matrix multiply a little bit. Talked about OSCI and its predecessor, sparsity for tuning the sparse matrix vector multiply. This searches over a design space of different FFT algorithms. The usual divide and conquer, even odd algorithm that I told you, the Cooley-Tukey FFT is the name of it, is not the only way to do it. In fact, since that paper was published, there have been over 100 papers published on different ways to do divide and conquer FFTs. And so there's an enormous design space to search. This paper won a prize for being a great autotuner, and it's very, very widely used. They added an MPI version back in June 2011 for the parallel case. And the latest version is from last November, and they added some bug fixes, and they did a better job of generating AVX code. So they're constantly updating it to take advantage of the latest changes in architectures. So here is some of their data. So it's a C library. It generates almost all the code automatically, 80% of it. And it's sort of going to do self-optimization. So it picks the best composition. So at each step, it may use a different divide and conquer algorithm, right? And at some point, it'll decide there's a base case, and it may unroll the code completely once you get down to, 16 or 32 sized FFTs. It'll stop doing recursion and just unroll it. And it'll decide the best layer to do that at. So let me just show you some performance data. And so there are so many lines on this plot because there are so many different FFTs that have been implemented over time. So each curve is somebody else's different attempt historically to write a fast FFT. And the one at the top, the blue line, is FFTW, which is usually the fastest. There are actually two different, and these are 4 different platforms and many, many different implementations. There are actually 2 different versions of the FFT. It's a little hard to read. One of them is out of place and one of them is in place. So out of place means that you take f times v, do the Fourier transform, and you write the answer somewhere else, and you do not change v. It's also possible to implement it where you overwrite the input with the output, where v gets overwritten by the FFT. That's called the in place. And they're implemented slightly differently. And both are on here. The solid line, I believe, is the out of place code. And the dotted line, which is maybe a little bit slower or faster, depending on the size, is the in place code. And there's also, for the platforms for which a library is available, MKL is on here somewhere. It'll come on a later slide, and we'll see the comparisons with MKL, with the hand-tuned Intel library. So you can see it's doing quite well. So it also does non-power of 2 sizes, not just powers of 2. And so in particular, yes, so both of these are 2 different platforms. And if you look at the horizontal axis, there are lots of different sizes besides powers of 2. So you can see how well it's doing there. And it will do best on powers of 2, but sometimes people don't always have that in their application. So it will do SIMD-ization. And so now we have the comparison with MKL. So this is an Intel platform. And this solid black line is MKL. And you can see that there are some problem sizes for which MKL is better, but there are other ones for which they do better because I believe this is handwritten. This particular implementation was handwritten, and it's hard to hand tune every possible dimension. But if you automate it, then you can get it, tune versions for every possible dimension. So here's the powers of 2, and you can see they do much better than for non-powers of 2 because most people don't have time to optimize that, right? So here is the way it works, but we've seen this kind of pattern before. There is something called a planner. It tries lots and lots of different decompositions at each layer in the divide and conquer, and it's going to pick the best decomposition by simply measuring it all, right? It's going to do auto-tuning. And what it does is it comes up with a plan, and it needs to store that plan so you can reuse it, because it takes a fair amount of work to do all that measurement, try all that. And so what it does is, for a particular value of n, it will hand you back, here's what you do at each layer. And then you can reuse that. So there's a tuning time, which takes a while. And then there is an execution time, which then goes very fast. So you have to, if you only want to do one FFT, then you probably don't want to wait for all of this tuning to go on. And then it also has a database of little codelets, unrolled code that it's going to use at the very bottom. So let me skip ahead here. So here is how you use it. And it looks very similar in spirit to the POSCI interface that I told you about. Then what you initially do is you say, I want to do an FFT. I want the input to be X, the output to be X. That tells you it's an in-place FFT. I want it to be forward as opposed to inverse. And I'm willing to do measurements, and it's of size n. Then it goes off and it produces a plan. And so this will take a while. This is where it tries all the different optimizations. And then once you have the plan, then you can reuse it whenever you need it. Okay, and then this can be done very quickly. So you can overwrite the vector x, execute the plan again, and this will be extremely fast. And then when you're done, you have to free it, of course. And so this is only worth it if there are going to be many transforms of the same size, as I was saying. So the next thing is that how do they deal with minimizing communication? They do not try to do explicit blocking. They rely on recursion. So what most algorithms do is, so here's the recursion tree, a size 8 FFT turns into 2 size 4s, which turn into, each of those turns into 2 size 2s. This is the same binary tree we saw before. What a lot of traditional implementations of FFTs do is that they do all of the iterations at this level. Excuse me, they start at the bottom, they do all the iterations at that level. So that would be one column in that pictures of butterflies that I had. They do all the first column. Then they go and do the entire second column. Then they do in the entire third column. And so what they do is they have to run through the entire array log p times, log m times. And so the memory traffic is m log m, and it's sort of as large as possible. So it's sort of a very bad way to traverse this tree. So what they do is that they do a recursion where they will do everything inside that block at once, everything inside that block at once. And then by doing it recursively, let me scroll down here, eventually everything down at the bottom will fit inside cache if you just do a depth-first search traversal of the tree as opposed to a breadth-first search traversal. And it will maximize, without you having to worry about what the cache size is, at every level of cache it will minimize the amount of memory traffic. Of course, once it gets small enough, it's unrolled, so for a particular platform, because you don't want to recurse down to 2 by 2. Okay, so it'll fit in the cache eventually. And this is an algorithm in the past we've called cache oblivious. It is asymptotically optimal. You don't have to know how many levels of memory hierarchy there are, and it's a good idea. So let me just scroll ahead quickly. So here is one slide on Spiral, which is an alternative auto-tuner. Their target is not just FFTs, they do that too, but all signal processing algorithms. So they have Viterbi and convolutions and all sorts of different things. And so at one point you could go to their website and say, here, I want this particular algorithm. You would type that in, I want this particular problem size, I want this particular hardware platform, and it would go run and hand you back your optimal code. So this was, a very attractive website, which is, now become a commercial venture. And so they're, trying to generalize it to many more other kinds of divide and conquer algorithms. So they were the ones who, took all 100-odd papers that have been published on different FFTs and coded them into a library. So they have a mathematical representation of all these different 100 divide and conquer algorithms, and they have an infrastructure which searches over that database of algorithms to sort of generate the right thing at each layer. So they take advantage of the beautiful structure of recursive structure of FFTs to describe the design space. So we're almost done here. So this is what we've been doing this semester. We've gotten through, I think, pretty much all of these 7 dwarfs now. And we're not done, we still have other ones to do, so we're going to have graph algorithms later. But we've now sort of finished talking about all these basic building blocks of high-performance computing. And I want to tell you what the rest of the semester is going to look like. So here's what all the lectures for the rest of the semester. And so I'm going to talk about dynamic load balancing on Thursday. So there are all sorts of techniques where if you don't have nice structure in your code and you want the system to balance the load and minimize communication for you, you have to deal with that. And then we will have a bunch of guest lectures on other topics, some of which are other motifs or patterns. So Aiden Bullish is going to talk about parallel graph algorithms. He has released a package called the computational BLAs, combinatorial BLAs, which are parallel graph algorithms based on lots of the techniques that we use for sparse linear algebra. Kurt Kreutzer will talk about structural patterns, not just the computational ones, but how do you glue together, individual implementations of all the computational patterns into higher level implementations. John Shelf from LBL will talk about frameworks. Some of you have already written about proposing to use Trilinos and PETSI and other similar frameworks for your class projects. People have been working on those for a long time to make it easy to write parallel code and have the framework hide all the details from you. Kristen Persson from LBNL has a project in computational material science. It's sort of Facebook for molecules, where people try to molecules try to find their friends to build bigger molecules in a computationally guided way so that people can discover new materials. Matej Zaharia, who's one of our own graduate students, who's built a lot of cloud computing infrastructure that's now widely used in Silicon Valley. We'll talk about cloud computing. Michael Weiner, who's a climate scientist from LBNL and involved in producing the every 4-year IPCC reports on climate modeling. We'll talk on world climate, what the future holds. He's going to talk about that. If you looked at the front page of the New York Times on Friday, March 22nd, the top of it was a picture of the universe that was produced here. You don't usually get those on the front page of the New York Times. So there's going to be a computational astrophysics project based on this new data that's been collected by an international collaboration called Planck with a bunch of satellites going up, measuring the cosmic microwave background radiation. And then the final lecture in the course will be the future of computing. What are exascale machines going to look like when they come out in the next decade, which are going to be doing 10 to the 18th operations per second. So that's what the rest of the semester holds. Plus your class projects, of course. Are there any questions? So that's a good place to stop.